All right, complexity classes. This is a topic that is near to my heart because sometimes the software engineering stuff can feel a little arbitrary. In like the worst case, like, oh dear, what is this system call named in order to like open a socket, or like in JavaScript, what is the particular behavior of the equals function when it's comparing different data types? And there's some like autistic sort of pleasure in mastering all that stuff, but with complexity classes and like the real CS theory, it feels like you're getting more at the secrets of the universe. And I like that. So let's dive in and see if we can untangle a few secrets. We're going to be talking about computation in its like pure form, and like what can we find out about the nature of computation. And this is the efforts of computer scientists over the last 80 years or so to try to map out the terrain of this question. Let's dive in. All right, so we are talking in this lecture about decision problems. And decision problems differ from ordinary algorithmic problems otherwise, in that they are strictly talking about yes or no answers. So here are some examples. Not a decision problem. Given some set S of integers, find a subset S prime such that the sum of all the entries of S prime equals 0. This is a form of the subset sum problem, and we'll see that in a bit. The decision problem version of this question is there some subset of S which sums to 0? We're not interested in finding it. We just want to know if it exists or not, and that turns it into a yes or no question. That's the decision problem version. So we are interested in decision problems here. And they, you can very often, frankly, almost always, write a polynomial time algorithm, which we will explore in a minute, to turn the decision problem solution into a, getting the proper answer to the question. Like, if we can know that there's some subset which sums to 0, then we can obtain the set of integers. So it's not entirely arbitrary, but it makes it easier for us theoretically to be dealing with these yes or no questions, because we do ultimately need to map out the terrain here, and dealing with all these different kinds of questions that require different kinds of answers, it's going to be impossible to compare apples to apples. Decision problems in this lecture. You have probably heard, or may have heard, of these things called P and NP. These are categories of decision problems, or sets of decision problems, in fact. P, which stands for polynomial, is the set of all decision problems with solutions that can be found in polynomial time. So you can find the answer to the problem, yes or no, in polynomial time. We can determine the answer. NP stands for non-deterministic polynomial. That's the set of decision problems with solutions that can be verified in polynomial time. So if someone gives you a solution and says, hey, I found a solution to this problem, and you don't want to just believe them, trust and verify, right? So you can verify that in polynomial time. It's easy to verify, even if it's not necessarily easy to obtain. So these are this is the dichotomy here. P is you can find solutions in polynomial time, and NP, you can verify solution in polynomial time. By the way, polynomial time, go back to the first lecture. Polynomial time is like constant time. You're never going to get constant time for solving a whole problem because you have to look at the whole input. There's at least n bits of input, so you got to have at least big O of n. But polynomial time includes things like constant time or log n time, or polynomials like n or n squared or n cubed, n to any constant. And things like n log n or n squared log n or n log n. There are some funky algorithms that have that kind of running time. Those are all polynomial time. Anything that is not exponential or sub-exponential. So, the big question, the famous question, is P the same set as NP? Is it the case that if you can verify a solution in polynomial time, then there is also an algorithm that can find the solution in polynomial time? I think if you think about it for a minute, you would find this equality puzzling. It is difficult to believe that just because you can check an answer doesn't mean that you can obtain the answer. We'll see many examples of problems in this lecture where it's pretty hard to find the answer, but it's also very straightforward to verify that you found the answer. So why would we think that P equals NP? Well, most people do not think this, but no one's ever been able to prove it. With all their effort, in fact, there's $1 million prize on the line. It's one of the Millennium Prize questions. If you can prove that P is NP or P is not NP, you can come home with a cool mill. We just don't have the machinery yet to address questions like this. But this is a really deep, fundamental question in computation, right? This is secrets of the universe shit. We're talking computation in general under any computational model, although we like to think about Turing machines and so on. If there's an algorithm that can verify, is there also an algorithm that can find in polynomial time? Well, we'll keep that question in mind going forward. The next thing to talk about is reductions. So, we have a reduction from problem A to problem B. We have an algorithm which can solve problem A using an algorithm designed to solve problem B. So if we've got some magic function that solves problem B, you can use it to solve problem A. Okay? So you could think of it, if you're thinking in my hopelessly software engineering brain. I got the software engineering worms eating my brain all the time. It's not comfortable, but they're in there. If you want to think of it this way, you can think of it as a function that takes as its arguments this B-solving function and an instance of the problem of A that you want to solve. And you can turn, and this function will turn the instance of A into something that it can pass to this fun-to-solve B function. This is a reduction. Solve instance of A would be a reduction from problem A to problem B. We're reducing these instances of problem A to instances of problem B. Okay? And if this algorithm exists, if we can write this function, and if it runs in polynomial time, we're not counting the call to fun to solve B here, but if the function itself runs in polynomial time, then we would say that B is polynomial time M reducible to problem A. M stands for many one. We often don't even say M reducible. If you're writing a scientific paper, you might want to be precise. We would just say it's reducible to problem A. Okay. This is going to be important going forward because we're going to be doing some reductions. We're going to be doing some examples of reductions. It's useful to prove properties about these computational classes, these complexity classes. There's a little bit more terminology here to go through. A decision problem is called NP-hard if there exists a polynomial time reduction to it from every problem in NP. So remember, NP is problems that can be verified in polynomial time. And if we can reduce all those problems to our potentially NP-hard problem, then it is NP-hard. So basically, we have this NP-hard solving algorithm in our pocket. Then we can write a polynomial time reduction to it from every problem in NP. And then another little bit of lingo is that a decision problem is NP complete if it's in both NP and in NP hard. So there's this universe of NP hard problems, and if a decision problem is also in NP, then we call it NP complete. It's that easy. A lot of terminology. Here's a diagram. Here's the case where P is not NP. This is what most people believe, although it's not proven. So P is down here. These are all our problems that we can solve in polynomial time. NP is all the problems we can verify in polynomial time. Notice that P is in NP. I mean, if you can solve it in polynomial time, then of course you can verify in polynomial time. It's already solved. You just solve it again. And you verified it. And since it runs in polynomial time, you can verify polynomial time. Cool. Here's the NP-hard problems. There's a bunch of them that are outside of NP, but the ones that are inside of NP are called NP complete. These problems out here can be just hard problems that are difficult to solve, that can't be solved in polynomial time, that can't be verified in polynomial time even. They might not even be decidable. There's some problems in computer science and in the theory here that are not even decidable. Like the halting problem is not decidable. You can't even come up with an answer, yes or no. You may end up with infinite loops that never terminate. That's the problem with the halting problem. You can't tell whether a program's going to terminate. So there's undecidable problems out here. There are problems that can't be verified in polynomial time. Just wacky problems. And some non-wacky ones too. There's some normal problems out here. But there are lots of NP-complete problems. These are ones that we're really interested in because they're in this similar universe of like, oh yeah, we can verify it quickly. But we probably can't solve it quickly if this P equals NP holds. Because P is down here, NP complete's up here. Here's the case where P equals NP. Everything in NP is also solvable in polynomial time. And of course, NP complete gets absorbed into that as well. Okay. There are other complexity classes that we're not going to cover that are more advanced, that we're just omitting. Okay. Here is the canonical NP complete problem. This is the big one. And this is the first problem that was ever proven to be NP complete. This is one that is very easy to reduce other problems to. And it comes up all the time. So let's go into it. This is called 3-sat. 3 satisfiability, or 3 Boolean satisfiability, I guess, in full. This is what a 3-sat problem looks like. This is the existential quantifier. It means there exists some values for A, B, and C, such that this expression holds. This Boolean logic formula holds. All right, so there exists some value for A, some value for B, and some value for C, for which this is true. And what does all this mean? If you're not familiar with, the mathematical logic symbols, the chevron pointing down indicates an logical or, like any one of these can be true, and the whole thing about it be true. A or. The chevron pointing up is and. So this is or and this is and. The or, you can think of it as like a bucket that catches everything. So anything around it, if any of it is true, then it's true. And this is and. Both sides have to be true. So you notice that we have these terms, or these conjuncts. Because this and operation is also called conjunction, and this is called disjunction, the or. So you have these conjuncts that are joined by ands, and each one is made up of a bunch of terms joined by ors. I've sort of mixed my notation here because I forgot to fix this, but this means the same thing. This means not C, and this means not B. The bar over the top and the little handle in front, they both mean not. So this is saying there exists some value for A, B, and C such that A is true, or B is not true, or C is true, and A is not true, or B is true, or C is not true, and A is true, or B is true, or C is true, and A is not true, or B is true, or C is true. That's what this whole expression means. So what makes it 3 sat is there's exactly 3 terms per conjunct. You can have as many terms as you want, you can have as many variables as you want. But there's exactly 3 terms per conjunct. There's these A or not B or C. There's 3 things here. And we can see that in fact this expression inside, this formula inside, is satisfiable. Because there's an example right here. A not, B, and C. So if we plug these in, A is not true, so this is not going to hold. B is true, so this is not going to hold, but we need it to be not true here. But C is true in our solution. So this whole conjunct, these ors, this whole term thing here, this is true because C is true. So this one's taken care of. We can ignore this for now. But we also have to have this term true. A is not true. Oh, we've already succeeded. So we don't have to care about whether B is true or C is not true. We've already succeeded. A is not true, or all this stuff. I mean, it doesn't matter what this stuff is. We've already got our A not. So go on to the next one. A is true, which is not the case. We got to move on. B is true, which it is. So we're good with this conjunct. And going to the last one. A is not true. Oh, A is not true. We're good. So we're done with this conjunct. So in fact, the whole thing holds. The whole thing is true. So there is a set of values for A, B, and C. There does exist these, such that all this is true. And here it is right here. A is not true, B is true, and C is true. I do have a question mark here. Any number of variables question mark? Because if you have fewer than 3 variables, how are you going to make meaningful conjuncts here, right? Like, if you just have A and B to work with, it's going to look like A or B not, or, I mean, you can only put an A or a B here. So if it's an A, I mean, it's redundant. You already have an A. If it's A not, then this whole thing's always going to be true because you've got A or A not. A is either A or A not, so it's always going to be true. So, you know, if you have fewer than 3 variables, you're being kind of silly. That would just kind of reduce to 2 sat instead of 3 sat. Okay. Let me get some water. Some pink lemonade. Okay. This is 3 sat. We're going to be reducing some things to 3 sat. Starting right now. CNF sat, this is conjunctive normal form Boolean satisfiability, reduces to 3 Boolean satisfiability. It drops the requirement that there be exactly 3 terms per clause. So this is a problem in CNF sat. Does there exist some values for A, B, C, and D such that A is true, or B is not true, or C is true, or D is true, and A is not true, or B is true? So here we've got 4 terms in this conjunct, and we've got 2 terms in this conjunct. So we've broken the rule twice. CNF sat does not require you to have exactly 3 in each conjunct. And we are going to prove right now that there is a polynomial time M reduction from CNF sat to 3 sat. Reminder what that means. We're going to be able to take something that solves 3 sat and use it to solve CNF sat. All right. And the thing we're going to write to do this is going to run in polynomial time. That's a requirement here. We are usually interested in polynomial time reductions. All right. So here's the same example from the last slide. There exists A, B, C, and D such that this is true and this is true. So we have 2 problems here. The first problem is that the blue conjunct has too many terms. So let's take care of that. This is the more complicated one, so I put it first. So there exists some A, B, C, and D such that this too big conjunct is true. And we are going to rewrite it. We can break it up into two pieces by adding another variable, which we're allowed to do. Remember, we can have as many variables as we want in 3SAT. We just have to have the 3 terms in each conjunct. So this is what we're going to do. We're going to add a variable e, and we're going to stick e onto each conjunct. But e is true in the first one, and e is false in the second one. And I would argue that these two quantified logical expressions are equivalent. One is true when the other is true, and it's only true when this one's true. Why is that? Well, we want to preserve this property that any one of these 4 can be true, right? Any one of these 4. A can be true, B not can be true, C can be true, or D can be true. So we can split it up. A is true, or B not is true, or E is true. We've got to stick a conjunction in there to make it look like it's 3SAT. But we can say, and C is true, or D is true, or E is not true. What have we done? We have put opposite E's in each one. So if A or B not is true, E is one thing. If C or D is true, E is the opposite thing. So if one is true, then E not knocks out the other one. It makes it automatically true. Same vice versa. All right? So we've preserved this property that any one of these 4 can be true by just swapping the sign on the E, or the inversion on the E. There's also the second problem, the red conjunct here, that it has too few terms. We can just kind of pad it out. This one's even easier. We just take, A naught or B is equivalent to A naught or B or B. This doesn't change anything logically, but we've put it in the 3SAT format. All right. This is our reduction to 3SAT. We can now use 3SAT to solve C and FSAT, just by rewriting it in the 3SAT format. And, by the way, this is a polynomial time reduction, because the size of the problem can at most, triple. If we give out a bunch of terms. And 3n is a polynomial time expansion in size. And we're just doing constant amount of work to do that expansion for each unit of growth, I guess you could say. So it's a polynomial time reduction. Let's move on to another problem. The vertex cover problem. We've got to kind of talk about some of these other problems and introduce them so that we have something to sink our teeth into, some kind of interesting problems to even talk about in the first place. So we did 3SAT. That was kind of interesting. You can use it to solve like Sudoku, for example. It's a satisfiability question of if I put a number here, is it still possible to solve the problem, to solve the puzzle? And you've got all these Boolean constraints. It's very natural. It very naturally reduces to 3SAT, or to SAT in general, which can reduce to 3SAT. Okay, so vertex cover. This is an interesting problem in graph theory. A vertex cover of a graph, G, which has some V vertices and E edges, is a subset V sub C of V, such that every edge is incident to at least one vertex in V sub C, in the subset. So we're taking a subset of the graph, and we want to make sure that every edge in our graph is incident to something in our subset. Here's an example of a graph down here. And we have chosen a vertex cover by surrounding them in red circles. So every edge in this entire graph, there's 1, 2, 3, 4, 5 of them, is incident to at least one of these vertices in our vertex cover. This one's incident to this one's incident to both of these. This one's incident to this one, this one's incident to this one, this one's incident to this one. Okay. The minimum vertex cover problem asks us to find the smallest possible vertex cover. There might be more than one smallest possible vertex cover. In fact, there is in this problem as well. We could have taken this vertex instead of this vertex, for example. But we want to find the minimum vertex cover. And this is in fact the minimum vertex cover. You can't find a vertex cover that has fewer than n vertices in this graph. So this is a minimum. But remember, we're talking decision problems in this lecture. So we have to have a decision problem version of this problem. The proper minimum vertex cover problem asks us to determine whether a vertex cover exists that has at most k vertices. So we're given some limit k and say, can you stay under this limit and still construct a vertex cover? So in this case, if k is 0, of course it's false. If k is 1, it's also false. If k is 2, it's also false. If k is 3 or greater, then the decision problem returns true. It's parameterized on k. And on the graph, of course. That's vertex cover. Here's another problem, the independent set problem. It is related. An independent set of a graph G with some vertices V and edges E is a subset V sub I of V such that no two vertices in V sub I are incident to the same edge. So here we're trying the same graph. We're trying to find vertices such that no two vertices in the set are incident to the same edge. So we've chosen this one and this one. They are, of course, not incident to the same edge. There's no edge between them. The maximum independent set problem asks us to find the largest possible independent set. And again, this is a maximum independent set. You cannot add another vertex here, and you can't find any independent set in this graph that has 3 vertices. I mean, you can try right now. Remember, you're trying to find a set of vertices, a subset of the total graph, such that the vertices in your set do not share common edges. You can't have an edge between any 2 vertices in your subset. That's an independent set. Of course, the decision problem version of this asks us to determine whether an independent set exists with at least k vertices. So there does exist an independent set with at least 0 vertices, so that would be true. There does exist an independent set with at least 1 vertex, and there exists an independent set with 2 vertices, with at least 2 vertices, but there does not exist an independent set with at least 3 vertices, or in fact anything greater than 2. So how are these 2 problems related? Why did I introduce them right after another? Because vertex cover reduces to independent set, and vice versa. Independent set reduces to vertex cover. Here's the insight. If we have a graph and we have some vertex cover, it doesn't have to be minimum, I should say, but some vertex cover, then all the other vertices form an independent set. And you can see that here. Arrange the vertices so that you can draw a circle around the vertex cover. So here we've put all the vertex cover vertices inside this circle. And you can just rearrange the way that you plot it on the page. So this is a vertex cover. That is, we have covered every edge in the graph with at least one vertex. At least one end of each edge is covered in the vertex cover. That's a vertex cover. So all these other vertices that are outside the vertex cover cannot have edges between them. If there were an edge here between these two red vertices, if there were an edge, then this would not be a vertex cover because we would not have a vertex incident to this edge in our vertex cover. So there cannot be an edge out here. There can't be an edge here. There can't be an edge between these two. All these vertices are just kind of sticking out like spokes into the vertex cover. So that makes these an independent set. There's no edges between them. That makes them an independent set by definition. That's what an independent set is. And in fact, this is the reduction, you know? A graph has a vertex cover of size less than or equal to k if and only if the graph has an independent set of size number of vertices minus k. So there's norm v vertices total, and there's k inside, so there must be norm v minus k vertices on the outside. So if this is a minimum vertex cover on the inside, if it is, it's not necessarily for this argument so far, but if it is minimum on the inside, that means we're contracting as few nodes as we can in there. As few nodes as humanly possible is going into this circle. And that means as many nodes as humanly possible have been left outside the circle. There's only norm v nodes total. I shouldn't say norm. It's the number of vertices in V. But you know what I mean. Does that argument make sense? If we do contract this vertex cover on the inside, then we have contracted it as far as we possibly can. Then that means we've left as many as possible on the outside. So this is our solution. A minimum vertex cover reveals the maximum independent set. They are the same problem. We can formalize it a little bit. Vertex cover IS VC. A graph with vertices and edges has a vertex cover of size less than or equal to k if and only if the graph has an independent set of size greater than or equal to the number of vertices minus k. And then we just write it in reverse. And we have shown both of these, I mean, with a visual proof, but I think it holds. It's convincing. So we've shown both directions of the reduction. And that there are polynomial time reductions. That's what the P means. You just collect up the vertices. So we can say the vertex cover problem is equivalent to the independent set problem. Any properties that we can say about the vertex cover problem also apply to the independent set problem when it comes to computational complexity, because we can reduce one to the other in polynomial time. Polynomial time is kind of, free. As far as our complexity classes so far are concerned. All right, let's do a tough one. We're going to do another reduction. This time we are going to reduce 3 set to independent set. So this independent set problem we just discussed, we're trying to find a set of vertices that have no edges between them. And we want it to be as large as possible. We want to know if there is, technically in the decision problem version, we want to know if there is an independent set that is greater than or equal to some k in number of vertices. So we're reducing 3-sat to independent set. So here's an example 3-sat problem that we're going to be working with. You can sort of just consider it to be generic. None of these are, without loss of generality, right? We're just kind of taking some example that can apply to anything. So here's our problem: A or not B or C, and A not or B or C not, and A or B or C. So we can construct this thing called a gadget. This is the actual word. It's a gadget. It's a graph that corresponds to the problem. And this is super, super, super common in reducing 3-sat to problems. Or reducing other problems to each other, actually. So, step 1 is to just draw out a triangle for each conjunct. And we label the nodes and the vertices in the triangle with the terms of the conjunct. So A and B naught and C. A naught and B and C naught. And A and B and C. Just like it is written up here. And then we draw edges between opposites. So A and A naught get an edge. A and A get an edge. B and B naught get an edge. B and B naught get an edge. C and C naught get an edge. And C naught and C get an edge. These all get edges if they're the same variable but they're opposite. This is clever. Because now we can ask, is there an independent set of size 3 in this graph? We pick 3 because there's 3 conjuncts up here. If we had more, if we had 10 conjuncts, we'd have 10 triangles. And we'd ask if there's an independent set of size 10 in this graph. And the answer to this question, is there an independent set of size 3, answers the original 3-sat question. Of if there is some values for A and B and C such that this is true. Why is that the case? Why can this answer our original question? Well, A and A naught are always connected. B and B naught are always connected. C and C naught are always connected. So if you choose A to be in your independent set, then A naught cannot be in your independent set ever. That's kind of like a constraint, right? This is like just logic. We're saying, we're using the graph to express the fact that A and A naught cannot both be true. They cannot both be in the independent set. That's what an independent set is. An independent set doesn't have any edges between its members. So A and A naught have an edge between them, and B naught have edges between them, and C naught. All these vertices that are opposites have edges between them. So we are constrained. We cannot pick both A and A naught. We cannot pick both B and B naught. We cannot pick both C and C naught. So we have to either pick all the A's or all the A naughts. We have to pick either all the B's or all the B naughts. And we have to pick all the C's or all the C naughts. This one. So that's sort of embedded or encoded this fact that we know about logic into our graph. The remaining edges express the fact that we just want to pick one of these to be true in each conjunct. Because we only need one of them to be true. I mean, more than one can be true, but for this problem, we're just picking one. And these edges ensure it, because they're all connected to each other. If we pick one, we cannot pick the other two. If we pick the C, then we can't pick A and we can't pick not B. So we are just picking one from each triangle. And if we can pick one from each triangle, that is an independent set of size 3, k equals 3, k equals number of clauses. If we can pick one from every triangle and it's still an independent set, that is, we haven't broken our constraint on not both being in their set, then we've solved the 3-set problem. If you pick C and A, not and B, then that would be our solution to the 3-set problem. Well, we don't really care about the actual solution, do we? What we're really interested in is whether it's possible to find a solution. That's a decision problem, right? Okay. This is a reduction of 3-set to independent set. Which means now that if we can solve independent set, then we can solve 3-set. And since we know 3-set is NP complete, that says something about independent set doesn't have. The other thing we have to check is that this is actually a polynomial time reduction. And it is. I mean, this is just translating this, which is just big O of k, or big O of n, really. Well, big O of k, sure. But, I mean, it's just a constant factor. The only interesting thing happens between these two steps, where we may have up to k squared new edges being drawn, order of k squared. So yeah, it does take quadratic work to do the extra drawing of edges, but it's still polynomial. So yes, this is a polynomial time reduction. So, in fact, we've just proven the independent set and vertex cover are an NP complete. So we reduce 3-set to independent set, so we know that independent set is NP hard. And we can actually verify whether a purported independent set solution is correct in polynomial time. So we know it is an NP. The way that we do that is you just check whether the independent set has greater than or equal to k vertices. That's criteria number 1. And check the no edges have both ends of the edge in the independent set, which is the definition of an independent set. We check that, we're done. So that just takes, linear work in the number of edges and in the number of vertices to count them. So this is a polynomial time reduction, and well, it's a polynomial time reduction so that we know it's in NP hard. And the independent set problem itself is verifiable in polynomial time, so it's in NP. And these two conditions together guarantee that, or are by definition, say that independent set is an NP complete. You go back to our diagram of what NP complete means. It's the intersection of NP hard and NP. So if it's in both NP hard and in NP, then it's an NP complete, by definition. And since the vertex cover is equivalent, it's an NP complete too. We've just proven something about vertex cover sort of transitively, going back to our equivalence proof from before. All right. So NP hard problems, vertex cover is, we've just proven it is NP hard. NP hard problems are supposed to be hard. They are hard. And vertex cover is, in fact, there's other additional theoretical properties of the vertex cover problem that say it's hard to even approximate. It's hard to get an approximate solution to the vertex cover. And that is bad news for us, because when we run into an NP-hard problem that we don't know of any solutions to NP-hard problems that run in polynomial time, we only have exponential time algorithms for these things. And so we often resort to approximation. Not always. Sometimes things can be manageable, but often we resort to approximation. And unfortunately, vertex cover is notoriously hard to approximate. There's a conjecture that you cannot approximate it very well in polynomial time. Right. You can approximate it very well with exponential time. Although such an algorithm is not known. You can get the factor down a bit. Anyway, so here's our clever idea for approximating vertex cover. This is, in quotes, clever. So we might think to ourselves, how do we approximate vertex cover? We would like to have the higher degree vertices, the ones that have lots of edges poking out of them, so that we can take care of as many edges as possible. Vertex cover, we're trying to cover all the edges with a set of vertices. So we think, okay, let's take vertices that have lots of edges, right? Say, oh yeah, let's take the one that has like 50 edges going off of it, because that's likely to be a better vertex cover than when you take a vertex that has just one edge poking off of it, right? It makes sense. But you can construct degenerate cases where out of bipartite graphs that cause this approximation algorithm to fall apart. In the worst case, it is off by a factor of log n. You might think that's not so bad. It's off by log n. But it is bad, because there's a very obvious approximation algorithm. This is our dumb idea. This is the student at the back of the class who doesn't pay attention. Raises their hand and proposes this idea. Just randomly pick a random edge. Just pick one. And then just add both vertices on both sides of the edge that you randomly picked. So you've covered the edge now. You've double covered the edge. And you've taken the two vertices and you just removed them both from the graph and all their other edges. And you put them in your vertex cover, just connected by that one edge. Well, there's no edges in a vertex cover. You're just taking the set of vertices. You just take these two vertices out of their original graph, delete all their edges, and then repeatedly do this over and over. Just pick a random edge and then pluck out the two vertices that are incident to that edge and put it in your vertex cover. And you just keep doing this until you run out of vertices. Okay? The thing is, you can only be off by a factor of 2. That's a constant factor. That's so much better than log n. Because no matter what the optimal vertex cover is, if you have some super smart person in the back, like, of the office, like, furiously writing away on their paper with a pen, trying to find the perfect vertex cover for you, every single vertex in their answer is going to be incident to these edges that you pick, right? That's the vertex cover definition. All you've done is take both sides instead of only one side. He's in the back trying to like frantically figure out which side is optimal to take, right? This one or this one, this one or this one. Just take them both, and you'll only be off by a factor of 2. And that is way better than a factor of log n. And there's a conjecture that a factor of 2 is the best you can do in polynomial time. So this super dumb, super easy idea is the best we know of. If you have more time than polynomial time, I think there was a result a few years ago that got down, well, let me get this right. There was a proof that you can never do better than a factor of square root of 2. So like 1.4 or something. 414, I think. But we don't know of anyone that of any algorithm or approximation algorithm that goes down that low. And it's conjectured that you can't get farther than 2. We know that you can't get farther than square root of 2, but in polynomial time. But the best we know of is a factor of 2. Okay, I think I got that right. All right, so that's vertex cover approximation. I want to run you through just a laundry list of other common NP-complete problems. And maybe I'll make some lectures about some of these at some point, I guess. I don't know, who knows. But these are all, this is like the flavor of like, if you run into this kind of problem, then you're thinking, excuse me, you're thinking, is this NP-complete? Because this sounds familiar. All right, let's run through them. Just get the flavor. First one. Does a given graph contain a Hamiltonian cycle? This is the Hamiltonian cycle problem. A Hamiltonian cycle is a cycle that goes through all of the vertices of the graph at least, or exactly once. So it follows edges in the graph that are already there and tries to go through every single vertex exactly once. All right. So the decision problem is, does a graph contain a Hamiltonian cycle or not? Because it might not. This is NP-complete. It's really hard. Second problem, does a given weighted graph contain a Hamiltonian cycle of some length less than or equal to m? This is the traveling salesman problem. So you're measuring the length of the Hamiltonian path as you go, and you want to know if it has, if you can do it, if you can make a Hamiltonian cycle in some limit of length before your car runs out of gas. Traveling salesperson is in a car and she might run out of gas if you go too far. So you want to know if you can do it in a length less than or equal to m. That's the traveling salesperson problem. Third problem. Does a given graph contain a complete subgraph of size k? It's the clique problem. So you got like a little star-shaped corner of your graph where all the vertices are connected to each other. And just figuring that out. If you're just given a list of vertices and their edges, right? And it's not all laid out prettily on the page where you can see the nice star pattern. To figure out this question of does it contain a clique or a complete subgraph of size k is NP-complete. Next one. Given two graphs G and H, is G a subgraph of H? That is, all the vertices in G can be mapped onto vertices in H such that there's edges in G where there's edges in H. And there's no edges in H where there's edges, no edges in G. This is the subgraph isomorphism problem. Next one. Can you color a given graph's vertices red, blue, and green, 3 colors, such that no two vertices sharing an edge have the same color? The 3 coloring problem. You might have heard of the 4 coloring problem. There was a famous result that got headlines in mainstream media a while ago. That this is the case for any graph if you can use 4 colors. That you can 4 color any graph. That is, like, color the vertices with red, blue, green, and pink, such that no edge has the same color on both sides. You can do that with any graph if you have 4 colors. But if you only have 3 colors, determining whether you can do that with a graph is NP-complete. Next problem. Given a multi-set S of integers, so a set that contain duplicates, that may contain duplicates, and some target number t, is there some subset S prime of S such that the sum of all of the S primes equals your target t? So you're given just a big bag of integers and you have a target number, often 0, if they're positive and negative. And you want to know if you can add up some subset of your numbers to hit the target exactly, like right on the target. So if your target's 0, for example, then you need to balance out like the positive and negative numbers so that it hits exactly 0. And you want to know if you can do that with the numbers that you're given. That is NP complete. It's a subset sum problem. All right, so this next one, I'm re-recording. This is future Riley Ann with her hair down. I had done this one before, and I went back and watched it, and I had a very cute analogy to explain it with gay polycules. And it was cute, but I think unfortunately it was also subtly wrong. So I'm re-recording. Let's see if we can get it right this time. All right, so given disjoint sets x, y, and z, disjoint meaning there's nothing in common between the three sets, they're just different sets. With the cardinality of the sets are identical, so there's the same number of elements in x and y and z. And a set of triples, x, y, and z, is there a subset of the triples which covers every element x, y, and z exactly once? That's a bit of a mouthful, right? And I can use an analogy to explain it. It's not going to be as cute as my gay polycule analogy, but I have one written down in my notes that will work. So this analogy is we are at a combination dating pool / pet adoption meetup where men and women have come to find a date and also adopt a pet. And this is the young Republicans only meetup where they're all straights, or at least they would never admit that they're gay. Half of them are gay, but they just don't admit it. So we're only having men match with women. All right. So everyone gets in this room and they look around and they see, oh, I could be with her. I could be with him. Oh, I could adopt that pet, sure. And they write down on a piece of paper their preferences. They're like, yes, my name is John and I could be with Jill and I could adopt Boots the cat. Or I'm Jack and I could be a Jill and I want to adopt Mittens the cat. And so they write down a list of all these possible matchings, right? And they hand them in, and your job is to try to match everyone. Give everyone a date and everyone a pet. And so that no one goes home, they paid the door fee. You don't want to send them home alone. So you have to find some matching out of all these triples. These, like, oh, John, Jill, Scrappy the dog. Like, these are triples. 3 pieces of information. And you want to find some subset of these triples that sends everyone home with a date and a dog. It sounds very silly. It sounds stupid. But actually, the first job that I had out of college, the sort of core component of the service that I was working on did basically not 3-dimensional matching, but n-dimensional matching on some, well, it doesn't matter on exactly what. But this is a real problem that arises in real software engineering. So, you can find a solution in some cases. You can say, like, okay, we'll send John home with Jill and Scrappy. And you're basically just, like, taking your highlighter and highlighting one row of, like, something that someone has handed in and say, okay, we're going with that matching. Because you have to do it that way. You can't, like, it wouldn't make sense to try to pick and choose. These are the only matchings you've had to choose from. You're just trying to find some subset of these triples that satisfies everyone. Okay? There's another note here. 3-dimensional matching is NP-complete. This is an NP-complete decision problem. But bipartite matching, that is 2-dimensional matching, is NP. And you can solve that efficiently. And I may make another lecture about it, or it might have been the last lecture. I haven't recorded that one yet. All right, back to past Riley Ann with her hair up. Given some unbounded number of strings, not like just a fixed number like 2 or 3, Do they all have a common subsequence of at least length n? This is the decision problem version of the question, right? We're not finding this common subsequence. We want to know if there exists a common subsequence of at least length n. A common subsequence is like a common substring, except you can skip characters. That's probably the only difference. So if you've got some substring and then a bunch of characters you want to skip and then another substring, and another of your input strings has the two like right next to each other, then yeah, that's a common subsequence. Even though there's some junk in between on one of those strings. There's no junk here, but there could be different junk here. There's a common subsequence. You can sort of read through one at a time, potentially skipping elements, potentially skipping characters, and they match up. So you're given an unbounded number of strings, not just two. Two can be solved efficiently. Thank goodness, because like 2- and 3-way diffs are critical to software development. But given some unbounded number of strings, do they all have a common subsequence, or at least like that? That's the longest common subsequence problem. And then the last one, the fun one. You know, these nerds, these CS nerds sitting in their high castle towers in like Cambridge or whatever, working on computer science questions. They like their a bit of fun once in a while, and they put out papers about trying to reduce common games to NP-complete problems to prove that they're NP-complete. People have done this with lots of games. And one of them is Minesweeper. It has been proven that Minesweeper is NP-complete on an unbounded grid. If you have a finite grid, then, I mean, you could just try all the combinations, and that would be polynomial, right? Well, you could sort of say, wait a second, there's a lot of combinatorics in there. But there is a finite number of potential combinations, and you can just run through them all linearly, just one after another, and you're just going to have a very large loop. It's going to be really large, but it's going to be bounded. And it'll still be polynomial in the size of the problem. I think that makes sense. Check the errata if it's not. I might change my mind later. Anyway, I'll show you an example of what I mean by Minesweeper here from the original paper of the proof. This is still a bit overwhelming, don't panic. But here are the 3 components you need to make a computer out of Minesweeper. First, there's a wire. You need to be able to get signals from one place to another in your computer. And this is what it looks like. Let's just look at the wire for right now. So here are some 0s and 1s. These represent the number of mines in the tile, in the square of the grid. X represents there could be a mine there, or there could not. It's a wire. It's supposed to carry a signal, right? So if X has a mine, it's a 1. Then X not, this little, there's a third notation for not, but that's what that means, X not. So if this one's a mine, this one can't be a mine, right? Because there's a 1 between them. You know Minesweeper rules, right? So this one can't be a mine. But then this one has to be a mine because there's a 1 up here. So this one's a mine. And then across the 1, this one can't be a mine. This one is a mine. This one can't be a mine. This one's a mine. So it's kind of carrying the information about whether this original X was a mine or not. Just across. And the wire just goes this way and carries that information. Once we've set this X as either, if we have some input into this thing, into this computer, then the data will flow through the wire. If we just either put a mine there or delete the mine, then it will update, it's not actually doing any computation, right? Nothing's happening if we run this in Minesweeper, if we construct this in a Minesweeper simulator. But logically, this one is connected to this one, and this one's connected to this one, and so on, all the way down the chain. Okay? This is a NOT gate. So if this one's not X, this one has to be X. of course. This is part of the wire that's just coming in still from back here. And all it's sort of doing, well, you can see that these two stars are, oh, I'm sorry, the ones and zeros aren't where mines are. They are, I misspoke before. They are like the numbers that are displayed in Minesweeper, of course. The stars are actually where mines are. So you've got two mines here. And so if there is a mine here, then that uses up all three, and this one can't be a mine. If there's no mine here, then you still gotta satisfy the 3, so this one has to be a mine. Plus these two, that makes 3. And then it carries through. So what you've done is you've taken like x prime x, or x naught, I should say x, and turned it into x naught. You've switched it around. This is a NOT gate. It's taking a signal and turning it into its inverse. I am definitely not going to go through the whole AND gate, but I trust that it's correct. It was in a peer-reviewed paper, so on. You know, well, okay. We'll give it to them on this one. You've got some input coming up a wire this way. If that wire is just rotated 90 degrees. This one, wire is rotated 270 degrees. And all the information carries through. And ultimately you get this T, which is the input up here and the input down here. V and U. Whatever V and U were, if they're both true, then T will be true. If one of them is not true, or both of them are not true, then T naught will be true. And it comes out the wire this way. So you may know from, well, just building digital circuits in digital logic design class or something, or from reading on the internet, that the AND gate and the NOT gate form a NAND gate. And NAND gates are the building blocks of CPUs. Because the NAND logical operation is logically complete. It can compute any of the other 2 input Boolean operations. So if you have not an AND, you have a NAND on your hands. And NAND is logically complete. So you can implement any logical circuit. You can implement a CPU. And if you can implement any computer that's doing anything at all, then you can implement a computer that solves 3-SAT. It remains to show that that's a polynomial time reduction. But, I mean, this is ands and nots. That result has long since been established. I thought that was neat. Someone's just being a little nerd about, they were probably, or he was probably just sticking around in his office playing Minesweeper and procrastinating on his work, doing paper reviews, and didn't want to do it, and thought, hey, I can make a paper out of this. And proved that Minesweeper on an unbounded plane is NP complete. This is fun. I mean, you can do this like in more places than you might think. Constructing these gadgets, again, is what they're called, to sort of make logical operations out of just like common, like computational looking things. All right, I think that is it for today. My throat is starting to give out. I hope that, wow. Excuse me. I hope that helped. And we'll see you in the next lecture, I guess, if there is one.